The biggest war in the history of physics was not fought on the battlefield, but in front of the blackboard. The two sides of the battle are the two smartest brains of mankind, Newton and Huygens. There is only one question in their debate. Is light an example or a wave? Newton said it was an example. Huygens said it was a wave. Two people quarreled for a lifetime. No one could convince anyone. In the end, Newton won. Not because he was right, but because he was more famous. The whole physics world has been misled by Newton for more than 100 years. Until 1801, a man named Thomas Young did an experiment and completely hit Newton's face. Light is indeed a wave, but the story is not over. In 1905, Einstein jumped out again and said that light is also an example. What? Light is a wave and an example. Isn't this self-contradiction? That's right. This is the craziest conclusion in physics. And this conclusion directly led to the collapse of human cognition of the world, because it proved one thing: logic does not exist in the microscopic world. To understand this crazy conclusion, we must first go back to the 17th century. At that time, humans began to seriously think about a question: what is light? Newton thought that light was made up of countless tiny particles. It's like a bullet shooting from the sun to the earth. This theory can explain many phenomena. For example, why does light go straight? Why does it reflect? Why does it refract? Newton was the god of physics at that time. He said that light is a particle. Everyone believes that light is a particle. But the Dutch physicist Huygens was not convinced. He thought that light was a wave, like a water wave spreading in space. Huygens' theory can also explain many phenomena, but no one listened to him because Newton was too famous. Throughout the 18th century, particles ruled the physics world until Thomas Young appeared. In 1801, the British did a very simple experiment. He opened two slits on a board and let a beam of light pass through the two slits. If the light is a particle, after passing through the two slits, two beams of light should appear on the screen, just like bullets passing through two holes. But the result shocked everyone. There were not two beams of light on the screen, but a row of lines of light and dark. It's like the pattern on a horse. This phenomenon is called interference. Only waves can cause interference. It's like two stones thrown into the water at the same time. The water waves produced will overlap. If there is a wave, the wave will be strengthened. If there is a wave, the wave will be cancelled. The interference of light proves one thing: Newton was wrong. Light is not a particle, but a wave. Thomas Young's experiment is called the most beautiful experiment in the history of physics. He concluded that the rule of particles for more than 100 years has become the mainstream since then. But the story is not over yet. 100 years later, another person messed everything up again. In 1905, a 6-year-old member of the Special Bureau of Statistics published a book called Einstein. He studied a phenomenon called the light-electric effect. What is the light-electric effect? Simply put, it's when you use light to illuminate metal. Metal will release electrons. This phenomenon is very strange. If the light is a wave, the energy of the wave should be related to the intensity of the light. The stronger the light is, the more electrical energy it releases. But the result of the experiment is exactly the opposite. No matter how strong the light is, as long as the frequency of light is not high enough, no electron can be emitted. On the other hand, as long as the frequency is high enough, even if the light is weak, electrons can be emitted. Einstein gave an explanation. Light is not a continuous wave, but a bag of energy. He called this energy bag a light-emitting bag. Later, it was called a light bag. The energy of each light is only related to the frequency. If frequency is high, the energy is high. If the frequency is low, the energy is low. So no matter how strong the low-frequency light is, the energy of a single light is not enough to kick out the electrons. This explanation perfectly solves the problem of the light-electric effect. But it also brings a bigger problem. If the light is a particle, how does Thomas Young's interference clause explain it? How can particles interfere? The answer is that light is both a particle and a wave. This is the second nature of glass. It sounds ridiculous, right? How can one thing be two completely different things at the same time? But the more ridiculous thing is still behind. Scientists decided to use experiments to verify this conclusion. They repeated Thomas Young's double hole experiment, but this time they turned the light gun into a dot mode. only one light is emitted at a time. A light can only pass through a hole. Theoretically, there should only be 2 beams on the screen. But the result was shocking again. As the light emitted one by one, interference clauses slowly appeared on the screen, etc. How is this possible? Interference requires 2 waves to overlap each other, but now there is only one light at a time. It can only pass through a hole. Who is it interfering with? The answer is even crazier. The light is interfering with itself. According to quantum mechanics, when you don't observe, the light will pass through 2 holes at the same time. It is in an overlapping state, both on the left and on the right. It's a wave and it's a particle. Then it interferes with itself. It sounds like a science fiction, but this is the result of the experiment. Physicists have to accept this reality. However, the real thing that makes people dizzy is still behind. Scientists want to know which hole the light passes through, so they installed a detector next to the double hole to record the whereabouts of the light. As a result, something strange happened. Once the detector is installed, the interference clause disappears. There are only 2 beams on the screen. The light acts like a pure particle. When the detector is removed, the interference clause appears again. The light becomes a wave. What does this mean? It means that the light knows you're looking at it. When you look at it, it's a particle. When you don't look at it, it's a wave. The observation behavior itself changes the behavior of the light. This is the most famous observer effect in quantum mechanics. It completely subverts the worldview of humans. In our daily experience, one thing exists. It exists. Whether you look at it or not, it's there. But in the quantum world, it's not like that. Your observation will affect the state of matter. Einstein was deeply concerned about this. He said a famous saying, "God doesn't know what to do." He didn't believe that the world was ruled by randomness. He thought there must be some hidden rules. We haven't found it yet. But another master of quantum mechanics, Bohr, didn't agree. He went straight back to Einstein. Don't tell God what to do. These 2 physicists debated this issue for decades. They didn't convince each other until they died. But the story is not over yet. In 1979, at the 100th anniversary of Einstein's birth, physicist John Wheeler proposed a crazier experiment. This experiment is called the delay choice experiment. Wheeler said, since observation will change the behavior of light, let's wait for the light to pass through the binoculars, and then observe what will happen to it. According to our understanding, when the light passes through the binoculars, it has already made a choice. Either go left, or go right, or go both ways at the same time. This choice should have happened in the past. How could it be changed by future observation? But the result of the experiment caught everyone's attention. In 1984, the University of Maryland really did this experiment. The result is that whether you put carbon dioxide in a detector, as long as there is a detector at the end, you will see particles. As long as there is no detector at the end, you will see waves. What does this mean? It means that your current behavior can determine the state of light in the past. The future affects the past. The law of cause and effect is broken. At least it looks like this on the surface. In fact, physicists have a deeper explanation for this. They say that before the light is observed, its state is uncertain. It is neither a particle nor a wave, but an addition of 2 possibilities. Only when you observe, the wave function will shrink. Only then will the state of light be determined. So strictly speaking, it is not that the future has changed the past, but that the past itself is uncertain. Until the moment you observe, the past will really happen. The father of quantum mechanics, Bohr, once said that before observation, no physical quantity exists objectively. This sentence sounds like philosophy, but it is the conclusion of physics, and it has been proven by countless experiments. The 2 physical nature of glass is not just the nature of light. Later, scientists found that electrons, neutrons, atoms, and even molecules, made up of hundreds of atoms, all have the 2 physical nature of glass. In 2013, scientists let the molecules containing 810 atoms pass through a double seal. As a result, there was also interference. The quality of this molecule is more than 10,000 molecules. Such a huge thing also shows waviness. So, why don't we see this phenomenon? Why does throwing a stone not cause interference? The reason is this. According to de Broglie formula, the wavelength of the object is compared to its momentum. The larger the momentum, the shorter the wavelength. For macro objects, their wavelength is short to the extent that it cannot be observed. A baseball's de Broglie wavelength is about 10 to the minus 34th square meter. This number is tens of numbers smaller than the atomic box. At this level, the waviness can be completely ignored. So the true physical nature of glass can only be observed in the micro world. But that doesn't mean it doesn't exist in the macro world. It's just that we can't see it. Back to the original question. What is light, wave, or particle? The answer is it is neither wave nor particle. It is an indescribable existence in our language. We can only say in some experiments, it acts like a wave. In other experiments, it acts like a particle. Nobel Prize winner Feynman said, "I can say with confidence that no one really understands quantum mechanics." The double wind interference experiment is called the core experiment of physics. Feynman said it contains the only mystery of quantum mechanics. From Newton and Huygens' argument, to Thomas Young's interference experiment, to Einstein's light quantum hypothesis, to Bohr's and Einstein's century-long debate, to Hewlett-Packard's delay choice experiment. For more than 300 years, humans have been questioning the nature of light, and the final answer tells us the world doesn't run as we think it does. At the smallest degree, logic fails, cause and effect becomes vague, and reality itself becomes possible addition. Perhaps, as Bohr said, if quantum mechanics doesn't surprise you, then you haven't really understood it. And this surprising world is the world of our real life.